Good morning, everyone. Let me begin by thanking the organizers for this opportunity to speak at this esteemed meeting. As you see from the title, I'll be talking about multifractional Brownian motion. But let's start by going back 2 steps and talk about fractional Brownian motion first, which is a canonical model of anomalous diffusion, very applicable in diverse fields. I list some of them here. In particular, very useful to model dynamics in viscoelastic systems, as you see from this picture, from this paper. And yeah. So you can think of it by thinking of the overdamped Langevin equation for Brownian motion, where it's driven by white Gaussian noise for Brownian motion, but now for fractional Brownian motion, the noise gets replaced by something called fractional Gaussian noise, which has these power law correlations as shown here, and characterized by this index called the Hurst exponent. The mean square displacement actually grows as t to the power 2h. And when h is between 0.5 and 1, you have persistent motion leading to superdiffusion. H between 0 and 0.5, you have subdiffusion. And when you put h equal 0.5, actually, then you recover back Brownian motion. So actually, fractional Brownian motion is a generalization of Brownian motion in that sense. And it has these characteristic features, namely this power law correlation and self-similarity property. And with this, it has been very successful to model a wide range of systems. However, over the last decade or so, with advancements in single particle tracking experiments, people now can track proteins and also organelles inside complex environments such as biological cells. And their fractional Brownian motion is insufficient, actually. And in one of such studies, when we analyzed the data of beads diffusing in mucin hydrogels, we used Bayesian analysis so that at the single trajectory level, we could compare a list of models to select the best model and also estimate the parameters, again, importantly, at the single trajectory level. And what we found is that most of the trajectories were consistent with fractional Brownian motion. However, when we looked at the estimated Hurst exponent, it seemed that the trajectories had different Hurst exponents. So in a way, we have to generalize now the canonical fractional Brownian motion, where the ensemble of trajectories all had one single Hurst exponents, but now you see a trajectory to trajectory variation of the exponent. And what we found is that, in this paper, that actually the distribution, at least in 2 cases we found, turned out to be the beta distribution as shown here. So in this paper, we generalized fractional Brownian motion to include this Hurst exponent changing from trajectory to trajectory. We considered a few distributions, including, of course, the beta distribution because of the motivation stated earlier. And interesting to note is that this beta distribution is actually quite flexible. As you see from this figure here, it can model both unimodal and bimodal distributions and so on. So, yeah. However, what we saw is that in more recent experiments, people also reported Hurst exponents that changes actually along a single trajectory. And this is the paper, and they tracked endosomes and lysosomes and found that the Hurst exponent can change along the trajectory randomly. Such evidence is also found in financial data. You can look at here. So now we have to go to the next generalization, which is to look at fractional Brownian motion generalized such that now the Hurst exponent can change along an individual trajectory stochastically. Mathematicians actually looked at this kind of processes, often through the spectral representation of fractional Brownian motion as shown here, and they studied several mathematical properties like continuity and so on. But to our knowledge, there lacked an analytically tractable model of multifractional Brownian motion. So this is what we do in our recent work, which got published, got accepted in PhysRev letters. We propose a multifractional model, which we call telegraphic multifractional Brownian motion, where we write a stochastic equation for h of t, considering it to be a smoothed telegraph process as shown here. So HTP is the well-known telegraph process, but now we smooth it and we have the smoothed telegraph process. An interesting property about this process is that in the stationary state, this has a beta distribution, which is what we were after. It also has some nice properties, and you can look at the mean and variance and also the autocovariance function, which will be important in what I will talk next, which has this autocovariance function of h of t has this exponential-like form as shown here. Now let's look at some simulated trajectories of h. So remember that the stationary distribution of h of t, which is beta, can be both unimodal or bimodal. We consider both cases here. The blue one comes from a unimodal distribution, the orange one from a bimodal distribution, and the corresponding multifractional trajectories are the top two here in blue and orange. And for comparison, you have the canonical fractional Brownian motion trajectories below. Now, if you look at this purple trajectory, which is a fractional Brownian motion, and compare with this 10BM trajectory, the topmost one, you see that visually they are very difficult to distinguish. So the next natural question is, when we have some real-world data, can we distinguish between these processes? And we propose to do that using the time average mean square displacement to estimate h of t and look at the autocovariance function. So for fractional Brownian motion, this should go to 0. For fractional Brownian motion with exponent varying from trajectory to trajectory, it should go to some non-zero constant given by the variance of the distribution of h that we will consider. And finally, for 10BM, we saw that it has this exponential-like form. And with simulations, we verify that indeed we can distinguish between these three classes of processes. We also found real-world examples for each class of this process. And you see here that when we look at the mean daily temperature data, then it behaved like fractional Brownian motion. Whereas when we looked at quantum dots tracked in cytoplasm of mammalian cells or beads tracked in mucin hydrogels, you see that the autocovariance function of the estimated h saturates at some non-zero value. Whereas when we looked at the day-ahead electricity price data between Germany and Luxembourg, we see this nice decay. So to summarize, we generalized fractional Brownian motion to include random exponents. We introduced MBM, where h of t is a smoothed telegraph process, and the stationary distribution, which is beta, turns out to be very relevant for experiments. And we also introduced a method based on the autocovariance function of estimated h to distinguish between these three classes of process, and we could find examples for all three classes. For more details, please have a look at the paper on arXiv now. Thanks.
Sorry, could you define the telegraph process? I don't know what that is.
So it's just, you have two levels, and there is switching with some mean rate. You just have two levels, and then switching with, given by these rates, lambda 1, 2, and lambda 2, 1.
So it's a two-state?
Yes, markup. It's a two-state, okay. But here we want a continuous change in h of t, not just two values.
Yes.
Therefore, we choose the smoothed telegraph process so that it can take, in principle, any value within these two bounds set by the two levels, h1 and h2.
So that's a process on 0, 1? On the interval
yes,
0, 1?
Yes, it's in 0, 1 because Hurst exponent naturally can take values between 0 and 1. But in principle, you can also set it to be different from 0 and 1. You just need two levels.
Okay.
So which is also a nice property of this because h is bounded by definition. And we wanted a stochastic process that is bounded also by definition. Otherwise, we need to impose some ad hoc conditions.
Mm-hmm. The usual telegraph process in what limit? When delta becomes what? From your beta distribution should become just some, there is a, for the usual telegraph process also there is a stationary state.
Yes.
So what limit I should take here?
I think the limit, when it goes to the bimodal distribution roughly, which should be, I think, yes. And one is on a yes. So you won't exactly get that, but what you would get is this roughly like this, the bimodal distribution with some very low probability for the yes, for the values there.
Around 2000, there were a series of papers by Bakri, Delure, and Musi.
Yes.
on a multifractal generalization of fractional Brownian motion.
Yes.
You look at the multifractal properties, not multifractional, multifractal of your work?
No, not yet, no.
Okay, we can discuss it
Yes,
later.
definitely, yes. I would love to talk more.
I have one question. Yeah. So in the standard fractional Brownian motion, the property is that the correlation, it has a very power law memory.
Yes.
So if I write down the xt1, xt2,
Yes.
which is this t to the power.
Yes.
Now you have h being the time dependence.
Yes.
So does with this h, the stationarity property that you have for the fractional Brownian motion, which is that time translation invariant.
Yeah, I think
does
this
it
is
lost now?
this is non-stationary now, yes.
Okay, so how
But-
does now xt1, xt2 look like now?
Well, we didn't have a closed form for this process, but what is interesting to note is that choosing this stationary state distribution for h of t, there is a theorem which says that this is still self-similar, locally self-similar. So that property still holds.
Yeah, so
Where-
there is self-similarity, but independent there is a stationarity property.
Yes,
And the stationarity property would be lost.
it
because
will
your
be
H-
lost, yes.
Your H is now.
Yes.
Okay.
Yes, so this is what you were asking for, right? The autocovariance function of. So here, if you put h to be constant, no time dependence in h, then you would get this is exactly for fractional Brownian motion. If you don't put this curly thing and remove the time dependences, this is how it looks for fractional Brownian motion. But now you have this additionally this,
Okay.
which clearly you are right. It ruins the stationarity property.
Thank you.
Any more questions?
Let's thank our speaker.